Okay. Morning, everyone. Morning, Hanshi. How are you? It's just the two of us for the moment, though I imagine some more will pop in shortly. All right. Week 12. We're all done with content. It's just review and preparation for the exam now. Some of you may have seen the announcement. If you haven't seen the announcement, please take a look at the announcement. So we have this session today. We're going to spend some time talking about the exam, talking about the course content in general, and anything that anyone wants to review or any questions that anyone wants to ask, please go ahead and do so. Please ask all of the questions. Any questions that you have, just go ahead and ask them, either in Echo or in Piazza. I'm watching, as usual. Yeah, and so let's just jump into everything, shall we? So, review week 12. What's happening at the moment? Okay, well, we have Programming Assignment 3. That's due in the middle of next week, week 13, SWAT week. Now, we don't have workshops during SWAT week because obviously it's the end of teaching, but we will be having a review session during one of our usual workshop sessions, and details of that are in the announcement from this week. However, we haven't finalized the location yet, but there will be an update at the start of next week, just a reminder about it, and we'll lock in the location then. So if you're interested in attending a review session, please by all means come along to that one. Make sure you make note of that one. It's not a scheduled class. It won't appear in your calendars or anything, so just be aware of it. As usual, well, same as last week, exam information is available in My Uni. If you have any questions that you want to ask about exam related stuff, feel free to do so in Piazza, but hopefully the exam information that is in My Uni covers pretty much everything. I'll try to answer any questions that people have now and in the review session, and if I get any more information from the university or from the faculty or from the exams office, I will be sure to post updates in there as well. Okay, that's pretty much that. What else is happening? CELTs are open, they're a thing. Feedback is always appreciated in any course that I teach. Contrary to what you might think, they actually get used. They get read on a number of different levels throughout the university. They get read at a university level, at a faculty level, at a head of school level, at a director of teaching level, and I get to read all of them as well. So I read all of my CELTs, and as I said, the school and faculty reads all of my CELTs as well. Whether they are good CELTs, whether they are bad CELTs. I think, whether they're good, whether they're bad, if they're constructive, they are much appreciated. As you probably guessed, this course has undergone quite a bit of change over the last couple of years, and that is in large part due to CELTs. The course content was severely out of date, as you've probably noted by the publishing date on the notes on finite state machines. Some of the notes and resources for this course are almost a decade, if not more than a decade old, and they've needed to be updated, and that's something we've been trying to do over the last couple of years, sometimes more successfully than others. So feedback on the things that you found useful, feedbacks on anything that you find has been good, what has been good, what has been bad, all of that. Please try to keep it constructive. That is the main thing that I do ask. I will happily receive negative feedback if it's constructive. If it's just Ian is a terrible teacher and nothing else, that's probably the most frustrating piece of feedback that I can receive. So I suppose if you really want to frustrate me, that's a good way to do so. But if it's just that, I mean, that doesn't help us make things better for future. So good feedback, bad feedback, we want to know what you think. CELTs are good. Yeah, I can't speak to every single course that we teach, but I certainly do use them in all of mine. Okay, all right, let's get on to some reviews. So much to cover, so little time. I mean, it is almost 2 hours. This is going to go one of two ways. There's only 2 of you currently watching this live, so we can cover lots of stuff or we can cover very specific things. So if you have questions, please go ahead and ask them. Or if you have areas that you want to focus on, please go ahead and ask those right now. Feel free to do so either in Echo or in Piazza so that we can see. I've started a live Q&A in Piazza there. What do you all want to focus on today? This is supposed to be a review session, so I want to focus on the things that you all want to focus on, because there was a lot, but all right, well, I guess we'll just start with a bit of a summary of all of the key concepts that we've looked at this semester, and then we'll get stuck into some past exams, and we'll take a spattering of questions out of those, and some other questions, and some general review advice. And if anyone has any questions at any point, just go ahead and post them or ask them. All right, so what have we done in this course? Well, hopefully by now we all have a bit of an idea of what event-driven computing actually means and a few of the different approaches that we can take to it. So we started off by considering this idea of basic state machines. How do we think of an event? Well, we think of an event as something that triggers a transition from one state to another. So your system can be in any number of different states at any given time. Well, not any number. Your system can be in any state at a given time. And we want to try to, we started by taking this approach using state machines of mapping out, okay, if my system's in this state at this particular point in time and I receive this event, what am I going to do? And we tried to map that out, starting off with DFAs, deterministic finite state automata. We would start out by mapping that out for all possible inputs into the system if we can. So we'd say, all right, well, here are all of the possible inputs. Here are the states that I'm currently in, and then we would try to map them out so that they would make some semblance of sense with all of the possible inputs. And we wanted to try to cover all possible inputs, not just the ones that we were interested in at any given time, so that it was very explicitly prescribed what should happen at every single step for every single possible input combination. So of course we started out with the camera being out of focus. Boop. There we go. And there we go, all right. So we started out with some basic states and transitions between them. And our states might have had names, and transitions belong to the event, whatever the event happened to be, that would transition us from one state to the next state. We had our initial states denoted by this lightning bolt, and our final or accepting states denoted by a double circle. So that was our basic finite state automata, and we expanded on this by saying, well, what if we wanted to be in multiple states at the same time? We know that the computer can only be in one state at once. I mean, excluding something like multi-threading, where the computer can potentially be in multiple states at the same time, but then we have to deal with race conditions and all of those sorts of issues. So to try to avoid that, we said, okay, well, we know that we want to eventually be in a single state at any given time. However, what if we pretend that we can be in multiple states at once? So we had the type of model where, okay, well actually maybe I can have either like two of the same transition off of a given state if I wanted to, and that would put me into a situation where if I received an A, I would go to two different states at the same time, and that's like, okay, well that's nice. So this is non-deterministic, so we called this a non-deterministic finite state automata, or NFA, rather than a deterministic finite state automata, or DFA. And we figured, well, we really need to make sure that eventually, if we use these higher level abstractions, that the system can actually handle them at a low level, which means we have to convert them back into a deterministic representation. And then the way that we went about doing that was by performing a mapping of states and transitions from the system in its regular form or in its non-deterministic form. So we would draw out a transition table, we'd map out all of the possible transitions, in this case it was just A, and then we would treat each set of states that was reachable as if it were a single state. So when the system is initialized, we end up here, A, like so, and then we would go through and we would follow every possible transition from every possible place, and we would just map it all out. So what are my possible transitions here? Well, it's just an A, so if I follow that, then I end up in these two states, A and B, at the same time. And we treat them as if they're one state, so that says, oh, okay, A with state A with an A gives us AB, and AB is an accepting state because B is an accepting state. And we would leave it at that, and we would map it out for all other possible inputs. Now, this was a very simple system that, well, actually, no, well, hang on. So AB with an A, well, this one goes away, but this one becomes AB again. I lied, it was AB. So, very simple system, because we have this looping element just here. And we could use that for some more advanced pattern and string recognition, but then we decided we wanted to try to take things to a little bit further layer of abstraction. So we added in these optional transitions that we may or may not want to take depending on the situation, called epsilon transitions. So we can use these in a variety of different contexts, but the way that we tended to use them was in regular expressions as a way to glue together components of a regular expression. So we mapped out the different components for the individual parts that might make up a regular expression, and then we glued those components together with epsilon transitions to create an epsilon NFA. So that might look something like this. Oh, sorry. Epsilon. There we go. So we have an epsilon there. So that means that if I'm in state B, optionally I could take this epsilon transition to put myself in this state for the purpose of taking another transition at some point in time. So if I had a C like this or something like that, that means if I'm in B, I can optionally take this transition to C from here via this state and through the epsilon transition. And we use that to build out our regular expressions that we saw in programming assignment 1. So that was that. We also talked about practical ways to build out these sorts of systems. We looked at the idea of merely machines, more machines, and merely more machines, which was okay, well, if we have a state machine, but I want to actually do something practical with it, for example, I'm trying to use it to, like, run a garage door or handle a car remote system, how might I build out a system to handle all of those components? So we had these three different representations. A merely machine where the behavior, so the question wasn't so much how do I move from state to state, that's implicit from the fact that we're using an FSA, but the question became, okay, well, how do I associate the actions, the behavior, with this movement from state to state? So we came up with a few different models, or we looked at a few different models. We had the merely machine where the behavior happened as part of the transition. So do X would happen there if we had, So if we receive a Y, we would do X on this particular transition. That was our Mealy machine, and that would be associated with every single transition. So every transition would have some associated, well, it doesn't necessarily have to have an associated behavior, but the behavior happens as part of the transition. So that was an X. Do Y. Something like this. So we would only perform each of these behaviors as part of the transition. So you exit the first state, you perform the behavior, you enter the next state. Or rather, this effectively happens on exit from the previous state before we enter the new state. The before is important there conceptually when we're dealing with a Mealy machine. Ultimately, we said, well, what if we wanted to have like the same behavior multiple times whenever we transitioned into a state? So if I had, all of the inbound transitions from various different places all had this do X behavior, and it's clear that like this do X behavior is associated with this state here. So instead of putting them on all of the transitions, we had an alternate model where the behavior was associated with the state rather than the transition. So we would have do X like so, and all of the transitions in would trigger this behavior on entry. This created a couple challenges for us because the behavior was associated with entry into the state in and of itself, as opposed to the behavior being associated with the transitions. It meant that if there was like a unique behavior that you wanted to perform for a particular transition, you couldn't do that within the constraints of a Moore machine, at least. So what you'd need to do is you would need to sometimes create duplicate states. So if I wanted to, for example, have a particular behavior that happens, do Z and then do X. So if I wanted to do Z behavior and X behavior on entry into this state, but only when I was coming from over here, then I'd have to create a separate state for it, and I'd have to do some extra linking together to make sure that the states all handle the behavior correctly, so that if this state had like an outbound transition over here, that because this is effectively a duplicate of this state, it also has the outbound transition over here. And if this state, we wanted to remain in this state for a particular behavior, we'd have to be careful with that, because looping like this would trigger this behavior every single time we entered back into that state, which we wanted to avoid. So then we might need another like dummy state that instead of looping like that, we would go down here, and again we would duplicate all the outputs from there. So for the use cases that it's suited for, that is avoiding duplicate code, very, very efficient, but also anytime that you want any differentiation from sort of a standard set, if the behavior itself isn't associated with the state, it creates a lot of extra work for us. So we then came up with this hybrid model called a Mealy-Moore machine, where we sort of took the best of both worlds and we said, well, why can't we just have state associated also with the transitions and with the states themselves? Which makes sense. So we could have that do Z functionality over here, and we could have do X associated here. And the other thing that we added was we added a way to basically loop back on the same state without re-entering. So if we recall, the problem that we had if we did this was that this arrow represents exiting this state and then entering back into it again. And when we exit and enter into the state, we always trigger this behavior. So instead of doing that, we added this thing called a partial transition, which represented staying put but not triggering these entry conditions. We stay in the state, but we don't trigger the entry conditions again. And that was Mealy and Moore machines. Then we started looking at concurrency, and we looked at this idea of how can we connect multiple finite state automata together, and we came up with a couple different ways that we could approach this. We had the idea of synchronizing two machines together through this sort of black box model, where if we had a DFA maybe that looks something like this, and if I had another one that maybe looked something like that, like so, that I could, and if this was X and Y on these inputs and this was A, B, and C on these ones, then we could potentially hook them together using some kind of black box approach. So we put each of them in a box and we say, okay, well, what if I wanted X to trigger whenever A triggers, for instance? So we would, if we considered this number 1 and number 2, we came up with this wiring model, X, Y, A, B, C, where we could say, okay, well, what if we link them together like this? And then we looked at, well, effectively this is just a fancy version of an NFA, because you have like 2 disjoint DFAs running at the same time. What does that look like? That looks a lot like an NFA. So then we looked at how we might evaluate that in the same fashion that we would as an NFA. We also looked at synchronization through the use of Petri nets, which we then used in our railway assignment. Hopefully I don't have to go into that in too much detail, but the idea of separating out the transitions and binding them together as things that are only allowed to occur when all of the input conditions are satisfied. So whereas if I had 2 distinctly separate DFAs like so, and I wanted to make sure that these are both firing this transition or these 2 transitions simultaneously, what I would do is I would bind them together like this, and this transition represented the idea that, okay, well, this transition can only fire when both this side and this side are ready to go, and then they go together. So we looked at that idea, and then we took it in an interesting and abstract way, which was using it to handle controlling of industrial systems. And in the case of RPRAC, we looked at how we could use it to handle signaling and point operation within a railway system. And we'll come back to these in a little bit more detail. We then moved on, we looked at the observer pattern. We started to look at how modern systems handle events. We looked at the idea of listeners, how to construct the listeners, how to set them up, this forming of dependencies and linking them together, and the registering and deregistering of listeners on objects so that when an event occurs, it can notify all of the things that need to be notified, even if it doesn't explicitly know what those things are when we write the program originally, or at least, when the program starts up, it may not necessarily know what things it needs to be notifying, but we put a mechanism in place to allow them to notify that. And then we ran with that concept a little bit further and stumbled into this idea of functional reactive programming, where rather than explicitly thinking of things as separate disjoint events, we start to consider them as continuous streams of events where you have events are potentially related to each other and they can come in succession, and we can handle them as a related stream of events rather than just individual disjoint events. And finally, we took that and we looked at how it might be applied in the context of a modern stream brokering service that's designed to handle lots and lots of different events firing all the time from lots and lots of different sources, and broker them all and manage them and provide additional features such as redundancies and tolerances, logging of data, windowing to handle different production and consumption rates of events and data, rate management, those sorts of things. So, wow, that's everything that we've been looking at across the semester, which, wow, that's a lot when I say it like that. So, that's a summary of everything that we've looked at. Let's take a look at some examples of what that means in the context of an exam. Before I do so, does anyone have any questions they'd like to ask? And if you have a preference as to where we start in terms of looking at questions on past exam papers, now's a good time to recommend, because I've got 3 past exam papers here. They're all 2-hour duration exam papers, and we have less than an hour and a half here, so we're not going to be able to do all of them, or all of the questions of even one potentially. All right, well, let's just start with some administrative stuff then. Please do ask questions again in Piazza or in Echo 360. I am watching both of them right now, albeit if try to post them in the live section of Piazza if that's the case. All right. So hopefully you've seen the previous exam papers that have been published online from this course, and hopefully you've had enough of a look that you can recognize which parts will or may not be relevant this time around. So things are going to look a little bit different for the people going remotely. It's going to be a MyUni style quiz, but the basic premise is going to be the same. Here is an example of what the paper is going to look like. You may notice a couple things slightly different from a past one. Here's a past one for reference. I'm going to zoom this out a little bit. I am already at maximum out zoom. Okay. Let's lift this up a bit. Alright, there we go. Okay. Alright, this is roughly what it's going to look like. Some things that you'll notice different from past ones. In previous ones, it looks something like this. There is no spot for you to write your name and details in the top corner. In a previous exam. This year's exam has that because you'll be writing all of your answers in the exam paper itself this time around. So you'll see that previously you would be getting a blank paper blue book where you would be writing your answers in there. Here you'll have space on the question book itself. So things to do when you receive your paper, well, follow all the instructions given once you get into the exam, but you'll need to write all of your details in the top corner of the exam paper here, and we'll also get you to write your student number on the top of each of the pages in the exam. This helps us with the marking process later on, make sure that things don't get mixed up. So things that you're allowed in the exam: yourself, writing implements, pen and paper, pens, pencils, erasers, those sorts of things. Generally recommend that you do most of this in pen, but for the diagrams kinds of things that you'll be doing, it's probably a good idea to go for pencil for those. So I recommend bringing pencil and eraser to handle those. You are allowed rulers and other drawing implements. You are not allowed to bring in calculators. Why would you need calculators for this course? You don't need calculators for this course. There's no kinds of questions that will require you to do calculations, or at least no calculations that should even be anywhere near remotely requiring a calculator. So if English is not your primary language, you are allowed a paper translation dictionary. However, those are subject to inspection and all of that jazz. So that's that. It is a 2-hour exam, 120 minutes. 120 marks. Now I know this is different than what I originally said. I originally said it would be 400 marks. That doesn't mean it's weighted any differently, that the number of marks are different. It's just, given that this is a timed exam, we went with the make the minutes match the marks approach. So every question that you do has some number of marks assigned to it. That number of marks roughly correlates with the number of minutes that we expect it to take you to do that question, at most. So if you're finding that you're doing a question and the question has been allocated something like, here we go, 105 marks, for instance. Not that you will get a 105 mark question. You won't get a 105 mark question. But if you find yourself spending more than 105 minutes on a 105 mark question, then you're probably putting in too much detail or too much work on that question. So use that to help guide the amount of time you spend on questions and to help you guide your pace. There will be clocks in the exam room that you can look at so that you are able to keep pace with how you're doing. Some of you have DAP arrangements, which means the amount of time that you have is different. Obviously, I can't change the numbers of marks that applies to, so just try to keep that in mind if it's applicable. I would recommend trying to pace yourself for the full 2 hours as normal anyway. That'll leave you some extra time at the end. So opening up the paper, you'll see that you have questions. Each question has some number of marks and a space to write your answer in, and I've tried to set up the spaces so that there will be also, in addition to the number of marks that you can see, the amount of space is also a bit of a guide as to how much effort you should put into an answer. If the question leaves you this much space and you want to write up like a paragraph that takes up this much room, that's probably excessive. If I've left this much space for you to write your answer, then I don't expect your answer to require more than this much space. And different questions of different weightings will require different amounts of space. So you'll have questions where you might be putting in short answers, questions where you might be putting in numbers or formulas. Probably not so much formulas, but you get the idea. A big question where you might draw a diagram or write a big long answer. You may get some multiple choice questions where you would need to fill in a box. So this would be the box. These are the boxes here, and you would just color them in like so, or put a big X in them or something like that. And finally, at the end of the paper, if you find that you have run out of space for a particular question or you need to redo something, there will be a couple extra pages at the end of just extra blank paper for you to fill in extra answers if you need to. If you do end up using these to fill in questions, it would be great. We'll check this, but it would still be great if you could indicate on the question. So for example, if you were doing this question here, whatever this question is, and you're like, oh, I drew my diagram, something like this, and you're like, oh no, that's terrible, I need to do it on the extra paper, please write like a note, see extra pages. We will check this, but it's just a nice little thing that also helps. And then you can do your answer in here. If you do an answer in here, make sure you indicate which question it was. So this was question 2A, so 2A, and then put your correct answer in and all that stuff.
Excuse me. We are allowed to use pencil here.
Yes.
We don't, right? Oh.
Yep.
So if we made a mistake, we can just erase it.
Yes, absolutely. Yep. Use whatever.
So it can be a right answer.
Preferably don't use red pen. I would prefer if you didn't use red pen, but...
I was planning to use pencil all the way.
Oh, yeah, pencil all the way is fine. Yeah. Yep.
Fine.
Yep. So was there
Like
a second part to that?
Even in the answers, pencil is fine.
Yeah, pencil is fine. As long as it's clear and easy to read. Yeah.
Okay.
I mean, it's like, obviously, if your handwriting is terrible, it's probably not going to be clear and easy to read either way, but you would be surprised what we can read when we're marking these things. Obviously, the easier it is to read, the easier it is to mark, and then the less likely we are to make mistakes while marking. So that's your motivation for not having terrible handwriting in the exam, but like, we get it. We're all computer scientists. You've seen my handwriting. You know what it's like. So I'm used to reading bad handwriting, and because I don't have to handwrite that much. And I wouldn't be surprised if it was the same for many of you. So we get it. It's fine.
Also, a last question about the boxes you were talking about.
Hmm.
You are expecting not to get more than the amount of the size of the box. Like the answers shouldn't be going out more than.
Yeah, don't write your answers outside the box. We won't be able to see them.
Oh, wait.
When I say we won't be able to see them, like the reason why there are explicitly boxes for answers on the exam, it's also the reason why it says to write in the spaces provided on the exam instructions. The reason why there are boxes is because we are using some special fancy software that helps us with the marking of exams. Not all of the exams that you'll be doing this semester, if you are doing other exams this semester, will be doing this. This is something new that we're trialing out. But it does allow us to do things like split out all of the answers to question 1 and review all of the answers to question 1 separately, as opposed to reviewing one person's question 1, then the same person's question 2, then the same person's question 3. So it makes for a more consistent and fair and equitable marking situation when all of the answers for all the individual questions are split out like that. Well, at least that's what we think, and that's what we're trialing. So, yeah.
Just the last question, because yeah, we all are students of computer science, except you, of course.
Oh no, I was.
Okay.
That's fine.
So the issue is like with me is like my words with a like handwriting are fairly I think it's like a little bit bigger, which is true. I try to make sense. Like my handwriting is not good, and so of course you are expecting everything to fill in the box like answers. Can we get another sheet to just complete our answers for the same question?
Like so again, there are these sheets at the back.
Yeah.
There'll be 2 of these sheets, which is just an entire empty page for you to write extra answers in if you've run out of space in the official answer spot. Again, as it says right there, when you do add extra answers on here, write the question number, so that when we go to look at this, we know which questions those answers are for. But there should be plenty of space in each of these boxes for you to write your answers, and hopefully that serves as a bit of a guide as to the amount of detail that I'm expecting on the answers as well. Yeah. Okay, so with that in mind, so that's the format for those of you sitting the paper-based exam. For those of you sitting the proctored exam, the questions are going to be the same, first of all, as the paper exam. It's just that it will be in the form of a MyUni quiz. So instead of having multiple choice like this, you would have a literal quiz multiple choice question, the same that you would do on any MyUni quiz. Instead of having a box for writing your answer, your answer in, you would be given a text input box that you can type your answer into for the proctored online exam. And for when you need to do diagrammy questions, you will be allowed to draw those out on blank paper, and you'll have an opportunity after the exam finishes to upload each of the diagram questions separately. So that's what's happening for the proctored exam. Please make sure you've reviewed all of the instructions provided by the university on that. Make sure that you have checked and gotten ProctorU installed and verified that it's all working before the actual exam. Doing it on the day of the exam, not a good idea. Make sure you've done it ahead of time, plenty ahead of time. There are, I believe, opportunities for you to test everything out and check that the proctoring system is working before the actual exam date. And again, the university should have provided you with details of that. If you are missing those details, or if you're not sure what I'm talking about, please post something on Piazza or ask me, and we'll try to track down the precise information that you need. Okay, so let's take a look at a past exam. Now I've got some choices here. For the 3 of us that are here, or 4 of us that are here, if you count me. So I've got 2019's exam, 2017's exam. You'll notice that the course code changed somewhere in the middle there. This used to be a third-year subject, which is part of the reason why there have been so many changes to the course. And I've got 2016's exam, which is not one that you will find on my uni, partly because it's so old and partly because I'm not going to give you like 20 past exams. That would be crazy. So any preferences as to which one of these we take a crack at, and any preferences on any of the questions that we would be having a look at for any of these?
To be honest, I had just a glance of the papers.
Mhm.
I didn't actually look into questions. I just wanted to see how big the exam paper gonna be
Mhm.
and how much time I'm gonna get it. That's it. To choose, I would recommend 2019.
2019? Any other thoughts from the people at home? I'm not seeing anything.
Everyone busy doing assignment week.
Probably, yeah. Definitely not seeing anything. Okay, all right, let's take a crack at 2019 then. I'll save 2016 for next week. All right, now, again, time-wise, we don't have time to do the entire exam. Or at least, we could probably do the entire exam in an hour, but not talking through it, at least. So, what have we got? We've got questions on FSAs. We have questions on DFAs, NFAs, regular expressions, epsilon NFAs, the old garage door from a Mealy or Moore machine. We have Petri nets. And we have the concurrency and synchronization. And then we ignore the rest of this paper because design patterns, graphical user interfaces are not relevant for this course anymore. So we can put those away. Where do we want to start?
Are you planning to finish all the exam paper within 1 hour?
Nope. Where do we want to start? Which questions do we want to look at?
Okay.
I'm not planning to do all of these.
Yeah, say, why not they starting from the last page? Like the bigger ones.
Start from the last page. Okay.
Because the small ones are easy.
All right. Okay, let's take a look. Oh wait, was there a page that I missed here? No, actually, that was it. It's hiding down the bottom here, the total. All right, okay, so what do we want to do? We want to specifically turn this into a DFA. Hopefully we're roughly familiar with how to do that because we've all seen how that works. So we have two of these, and the way that I would approach this, I mean, there's a few different ways that we could approach this. We could approach it just by translating the transition table directly, or we could draw out a diagram if we wanted to. I'm just going to do the transition table directly. So we have Q, R, S, and T as our inputs, like so. Q, R, S, T. And then we just play through the system with each of these inputs at every single step and see what we end up with. So the system initializes into Q1 on the top machine, Q1 on the bottom machine because they're both the same. So we're going to call that Q1, Q1. And then we just play this through. We say, okay, well, if I'm in Q1, Q1 with a Q, which is A on the top machine, C on the bottom machine. So A on the top machine, C on the bottom machine. Now this C doesn't go anywhere, and if we recall in these systems, if it doesn't go anywhere, the system is null and void at that point, so nothing happens there, or at least the system dies at that point for Q from Q1, Q1. What about R? R from Q1, Q1, well, on the top machine, R is a B, which gives us a Q3, so that's going to be Q3 on the top machine, and it doesn't feed into anything on the bottom machine, so the bottom machine stays put. So Q3, Q1. And we're going to add that as a new state. All right, and then let's take a look at S on Q1, Q1. So C on the top machine, A on the bottom machine. Again, doesn't do anything. T gives us B on the bottom machine. That's going to be Q1, Q3. So Q1 on the top machine because it doesn't go anywhere, Q3 on the bottom machine. And then we keep going. If we're in Q3 on the top machine and Q1 on the bottom machine, and we get a Q, so Q3 with an A is no. Q3 with a B, because it's B on the top machine, Q3 is a no. S is a C, so Q3 with a C is Q1, okay. And the second machine, which is on Q1 with an A, is Q2, so this is Q1, Q2. And then T, which is a B on the bottom machine, so if we're in Q1 on the top machine, we get a B, so that's going to put us in Q3, Q3. And then we add these new states down the side here. If one of these states was a finishing or accepting state, make sure that you flag any state here that has a finishing or accepting state in it in this table. So if we said Q3 was a finishing or accepting state, then any of these states that contain Q3 would also become finishing or accepting states. Not that you'll probably see that. And then you just build out the table going all the way through. The reason why you don't just try and list out all the states first and then build the table out is that some of the states you may find are unreachable, so you explore the table out as you go and build out each of the rows as you come to. In theory, the maximum number of states that you can have in a system like this is, oh, what is that? Is that 9? Or is it 6? Maximum combination. There are 3 states in the top machine, 3 states in the bottom machine. I think that's 9. Yeah, I'm going to say that's 9. So number of states in one machine multiplied by the number of states in the other machine, that's the maximum, theoretical maximum number of states that you'll have in a system like this. So at most we will have 9 states in this system, but there will probably be some that are unreachable. So realistically, hopefully we only have to build out to something like 7. I'm not going to build out the rest of it because of time, but you get the picture. All right, working backwards. Petri nets. Consider this Petri net here. Draw a state diagram for the DFA that is equivalent to this Petri net. Very much the same process with the Petri net. You figure out what the initial state is and you step the system forward, taking all possible routes that you can take. This one says to draw a state diagram, so I'm going to go ahead and draw a state diagram instead. So let's start off. Now the system starts off with 1 token in P1, 1 token in P2, and 1 token in P5. I'm actually going to pull out my tokens for this.
Okay, I think it's easy. I don't want to say this.
If they didn't stick together. All right, so P1, P2, P5, which we can represent arbitrarily as P1 is 1, P2 is 1, P5 is 1, and all of the others are 0, or just as 1, 1, so 1, 1, P3 is 0, P4 is 0, P5 is 1, P6 is 0. So we can represent it just as this, as the starting state. Alright, and which transitions are enabled at this point? Well, the only transition that is enabled is T1, so we can take a T1, and if I take T1, then we end up with, now note the 2 here, so that means that these 1 goes in, 2 go, I'm just picking all the wrong tokens today. Alright, so 1 goes in, 2 goes out. So we end up like this. So this is going to be 1, 0, 2, 0, 1, 1, 0, 2, 0, 1, 0. Okay, and then what transitions are enabled from here? Well, T2 is enabled. No other transitions are enabled, so we can take a T2, and that's going to put us into this configuration here. So that's going to be 1, 0, 1, 1, 1, 0 with a single T2, like so. And then what transitions are enabled from here? Well, we have T3, which is enabled, which can take us right back up to here. Or we have T2 is also enabled, or T4 is enabled. So let's take a look quickly at T2. So if we do T2, we end up like this. And that gives us 1, 0, 0, 2, 1, 0. 1, 0, 0, 2, 1, 0. Alternately, if we step it back and if we take T4, we end up like that. 1, 0, 1, 0, 1, 1. Zero, 1, 0, 1, 1, and so on and so forth. You keep building this thing out. Things we want to watch out for when you're building out a Petri net like this, if you find yourself, if you find a state that's just hanging by itself with no outbound arcs, that's a deadlock state. That's just something to be aware of, because if there are deadlock states, there's a reasonable chance that you might get asked questions about them. Similarly, watch out if the system is unsafe. That said, it would be pretty cruel of me in an exam to force you to map out an unsafe Petri net into a state diagram, considering that an unsafe Petri net would result in an infinite state diagram. So if you were to get a question about an unsafe Petri net, you would probably get some form of indication that the Petri net might be unsafe before you get asked to perform any form of conversion on the Petri net into a DFA. So those are some things to bear in mind. Okay, consider the marking. P1 is 1, P3 is 1, P4 is 1, and P5 is 1. Well, let's see, have we actually hit one of these yet? Here, yeah, it's there. So, is the marking reachable? Well, once you've done your DFA conversion, you should have a map of all of the possible markings that were reachable in the system. So if it's in that DFA, then it is reachable, and that is how you can explain it. That is part of the explaining. You can say, okay, well, it's clearly here in this DFA. I would reach the marking by, and then you would just write out the shortest sequence of transitions to get from the initial state to the desired marking. Which transitions are enabled from the marking? Again, look at all the outbound arcs from that marking on your DFA, and once you've located all of the outbound markings, or all of the outbound arrows from that marking, that'll tell you which transitions are enabled. In this case, this is the marking just here. P1 is 1, P3 is 1, P4 is 1, P5 is 1, and you can see that we have T2, T4, and T3 all enabled. What is the largest value for B for which this Petri net is B safe? you're looking at the individual digits in here and you're seeing if you're finding the largest digits basically. So yes. And we talked about deadlock already, so I'm going to leave that there. All right. Mealy machines, more machines, and merely more machines. You can get asked to design any of those three types of machines, and if you do the wrong one, you're gonna lose most of the marks. So don't do the wrong one. If I'm asking you to design a mealy machine and you design a more machine, that is not what the question was asking you to do. You'll get some marks, but you will lose most of them because you were explicitly asked to draw a machine of a specific type. So make sure you're familiar with the differences between them. Really should have brought water with me today. Oh, anyway. All right. Realistically, probably not going to ask you to write code in an exam, even though that has been a question that has been asked previously. So that's just something to note there. But you probably would get asked, for example, to design a mealy more or mealy more machine. Again, make sure it's the right one for a particular system. So take your time. You will have additional scrap paper. So in addition to the booklet itself, which has space for you to write in, you will have some extra blank paper that you can write on. If you need to sort of scratch out a rough design on there and then transfer it over, feel free to do so. Don't put too much time into your draft design because we don't want to be in a situation where your draft design is on the scratch paper and then you run out of time and it's not actually in the exam book, because I can only mark you on what is in the exam book, not what is on your scratch paper. Oh, got an all phlegmy here. Okay, so when building out a... Come on. There we go. Yep, okay, alright, so when building out a system like this, as we talked about in some of the examples, start by figuring out what all of the inputs into the system are, and then try to figure out what all of the different states are from the description. So in this case, I'm going to try and identify all of the different inputs into the system. So what have we got? Well, we have, in terms of, well, we also want to identify the outputs. So what does the system have? Well, the system has a motor, that's an output, an alarm that beeps, that's an output. I think that's about it. We'll come back to that and see if there are any other outputs as we go through. We have a bumper switch, which is an input. We have a sensor that indicates when the door is open, that's an input, and a sensor that indicates when the door is closed, that's an input. And a remote control device with one button on it, so a button that a user can press. So these four, the switch, the open and close sensors, and the button, those are our four inputs into the system. That's our alphabet of this system. So we need to account for all of those in all situations when we map out how the system is going to work. Take a read of the scenario, try to get a sense of the basic behavior that the scenario is describing. Make sure you're clear on what the correct behavior actually is. Try to avoid making assumptions where possible, and if you find that you have to make an assumption in order to build the system as specified, state what that assumption is. If you come across anything ambiguous, you're not sure about it, state your assumptions. As long as you have reasonable assumptions, you will not lose marks if you do make assumptions. If your assumptions are completely unreasonable because you don't understand the basic premise of what you're being asked, or if you do not understand how to draw a merely more machine, for instance, then yeah, your assumptions are probably going to be wrong. You're not going to get marks for those, but it's a good idea just to write down any assumptions that you have anyway. So in this case, we say when the controller is first connected to power, the alarm beeps 3 times and the motor operates to lower the door until fully closed. We've been asked to draw a Mealy machine. So if I take some paper here, so we would want to start off our system by creating an initial state of some sort and mapping in the actions that we want to take. In this case, we want to beep the alarm 3 times and start lowering the door. In this case, I'm making the assumption that the alarm is something that I can trigger to beep a certain number of times. And having seen the various examples in the course notes, that's a reasonable assumption that you could make as well. But that is an assumption that I might want to state when I'm stating my assumptions. So now my motor is running and my door is lowering itself down, so that's this state here. So the door is in a lowering state initially. And then we're going to step through the rest of it, so I'm just going to call this lowering. And let's take a look at, and so it operates to lower the door until it is fully closed. So it's put the door into this lowering state, and the door is going to continue to remain in that lowering state until the door is fully closed. How do we know that the door is closed? The door is closed when the closed door sensor is triggered. And that's going to put us into the fully closed state, like so. And then we would just keep building our system out from here. We want to make sure that we cover all possible inputs, and if we have to split an input based on some sort of condition, that we've covered both sides of that condition. I'm going to leave that one there. If anyone has any questions, please do ask them now. Okay. All right, regular expressions. Write a regular expression that represents the set of strings over 0, 1 that contain at least 5 ones. Okay. You've all done work with regular expressions, so the basic syntax of a regular expression should be somewhat familiar. If you're not familiar with the basic syntax of a regular expression, get yourself familiar with the basic syntax of a regular expression. So we need a set of strings over 0 and 1 that contain at least 5 ones. So we need at least 5 ones. This is a little bit tricky because the 5 ones can be anywhere in the string. So really what we need is we need like a 1 and then some number of zeros, whether it's 0 or more zeros. So 0 or more zeros, a 1, 0 or more zeros, a 1, and 2. Yes, this one is that simple. That'll be it there. And how we get to this answer is we just want to think about all of the possible ways that you could reach that string, and we want to try to construct a regular expression for that. That's a little bit tricky. And it's a bit outside of what we've been particularly covering this year. So we're probably going to focus a little bit more on the epsilon NFA side of things, but we might still wonder about like the alphabet, strings that belong to a regular expression. So a question like B wouldn't be entirely out of the question here. So in this case, making sure that we understand the order of operations for regular expressions. So in this case, checking which of these strings matches this regular expression. So firstly, it helps to understand what this regular expression is asking. It is 0 or more A's followed by at least one B, or just a C. So let's take a look at, well, let's draw this out as an epsilon NFA just for fun, so that we understand what we're looking at. So we have C down there, and then we have A star, this is the simplified version of the A star, followed by B plus, like so. And then that's our accepting state. And here's our initial state, like so. There's some epsilons in there, so that's what that looks like. So let's try and step each of these through here and see what we get. So A followed by B followed by C. So if we start here and we do A, we end up here, so we can do that and follow this, and we end up here like so. So that's with A, followed by B, well that puts us there, followed by C. Well, there's nowhere in this system for a C once we're here, so it's not going to be that. Oh, I lied. Hang on, I missed the extra brackets and the star just here. Sneaky. Make sure you see the entire question. That's always going to help. So epsilon there to a final state there and an initial state here with some extra epsilons for good measure. Okay. Okay, so A star followed by B, which we did get, or C. So A star followed by B, which gets us to there, and then we can loop back around and we get the C. So that one actually is correct, okay. A followed by C followed by B, well, if we come in the first time, we get A followed by C. Well, there's no outbound C from an A. That is a problem, so that one is a no. B followed by A followed by C. Well, again, there's no AC. That's not good, so that's going to be a no. B followed by C followed by A, so we have B to start with. So if we follow our epsilons around here, we can take a B from the start via this epsilon closure just here. That's good. And then a C back around, that's a C just there, and then an A. We can't finish on an A, so that's a no.
C followed by A followed by B.
What do we reckon about that?
C is already, it's gonna be no, yeah. Because we are checking the whole string, not just the first, the characters. So if we are checking the whole string, that means it's false. We are checking just first characters, like whatever comes first, and we are passing it, and it's correct. Because C is going to.
So in this case, it says strings that belong to the language of the regular expression. So that means that we're looking for an exact match here.
So it means no then, isn't it?
Well, okay, so if we follow this around, we can do C through these epsilon transitions here.
Yeah.
And then we can loop back around for an A, followed by a B, and that does put us in our accepting state. So that does put us in our accepting state here. So that one does actually work. And this one does not, for the same reason that this one does not. This one does not, but this one does. So it will just be these three that do. Now, oh, we have had a question in Echo 360. What have we got? For 3A, the question says at least 5 ones. We need something like that at the end. Yes, yeah, we probably would need something like 1 or 0 star at the end. In fact, we could probably omit the 0 star because that's sort of covered here. And if we wanted, we could also... Actually, no, that's fine. Yeah, that would work. We wouldn't want 1 star, 0 star because without the or symbol in there, because otherwise that only expects a sequence of 1s followed by a sequence of 0s. It doesn't allow for multiple additional alternations back and forth. Although you know what, actually that does, never mind. That works. Not the most efficient way of doing it, but it absolutely works, yeah. Nice catch. Alright, draw the diagram of an NFA or epsilon NFA that accepts the language of the following regular expression over the alphabet 0, 1. Alright, so 1, 0 star, 0, 1, 1, 0. Hopefully we're all up on that. But let's just draw it out real quickly. So if we had 1, 0 star, draw my initial state in like so, and then 0, 1, 1, 0, so 0, 1, 1, 0, like so. So 1, 0 star, 0, 1, 1, 0, accepting state. Extra epsilon NFAs or extra epsilon transition story are fine if you want to throw some extra ones in there for that question.
Just a question.
Mm-hmm.
Okay, yeah. So we just have to draw the diagram. Do we have to explain something because it's worth of 6 months? Just draw the diagram. That's it.
Let's just draw the diagram. If the question just asks you to draw the diagram and doesn't ask you to explain anything, then just draw the diagram. Again, if you have any assumptions that you are making that you're not sure about, state those assumptions while you're next to your diagram that you draw. But yeah, if it just says draw a diagram, that's all you need to do. All right. Okay, explain how the 5-tuple definition of an NFA is different from the 5-tuple definition of a DFA. Well, the difference between an NFA and DFA, of course, like ignoring the 5-tuple definition, you could probably get at least one of these 2 marks just by stating the difference between an NFA and a DFA, maybe. And probably half a mark at the very least. What is the difference between an NFA and a DFA? I mean, just stating that one is deterministic and one is non-deterministic is not quite enough there, because that doesn't demonstrate that you know what that means. So at the very least, you would need to demonstrate that you know it. So the question says, in the formal definition, explain how the definition of an NFA is different from the 5-tuple definition of a DFA. So knowing what the 5-tuple definitions are does actually help. 5-tuple definition is... Oh, crap. I believe it is something to the effect of, so for a DFA it is D equals, oh, what have we got?
Yeah, I mean.
Okay, so capital Q, which is the set of states, I think. We'll check this in a moment, people. Capital Q, which is the set of states. Capital Sigma, which is the alphabet. I may have the order wrong on these, not really fussed over the order. Lowercase q naught, the initial state. Uppercase F, the set of finishing states. And delta, the transition function, lowercase delta, the transition function. Now for an NFA, it differs a little bit. Looks something like this. Q and sigma are going to be the same, but Q naught is uppercase Q representing the fact that we can have multiple initial states, so it's the set of initial states, the set of final states, and actually I think delta is the same. Let's check this.
So that's why we need to
So
talked about in our answer, yeah.
for full marks, you would say this is the 5-tuple definition for a DFA, this is the 5-tuple definition for an NFA. They differ in the fact that Q naught in an NFA represents a set, whereas Q naught in a DFA only represents a single state, which reflects the fact that the NFA can be in multiple states simultaneously. I think delta might be uppercase in an NFA. Let's just double check that. As you can probably tell, though, I haven't been too hung up on formal definitions of the formal algebraic definitions in this course. So while 2019 version of this course was a little bit hung up on them, I am certainly less so as we've been going through this course. 5-tuple definition of an NFA 15. Okay, Q, sigma, transition function denoted as delta. Okay, it is lowercase delta. Set of start states is capital Q, so I think that's pretty much it. I got the order slightly out, but no one's really counting with the order. Or at least I'm not going to be counting with the order. Let's take a quick look. That's the formal definition of a DFA. Although they've used M for it here, but as we can see, yep, exactly the same, except in the case of a NFA, it is capital Q representing a set, lowercase q. So as long as your answer recognizes the fact that in a NFA it's non-deterministic, which means that we can be in multiple states simultaneously, whereas in a DFA we can't be. Even if you don't get the full formula, you would still get marks for that. Alright, draw an NFA or epsilon NFA that accepts a set of strings that contain either an even number of ones or an odd number of zeros. Both can hold at the same time. Alright, so we need even number of ones or an odd number of zeros. Or both. Let's go with a basic NFA. So let's start with odd number of zeros. So initial state. Now, if we were in initial state and we wanted to get to an odd number of zeros, what are our options for getting to an odd number of zeros?
What do you mean?
So we're in our initial state. We want to get from, we want to accept strings that contain an odd number of zeros. What are our possible options for going from nothing to an odd number of zeros? In terms of a single input that we could take.
So it can either go to the next step or just stays at the same place.
Okay, but how is it going to stay at the same place?
Oh, okay, if we receive
So
this,
what is our alphabet and what are our possible transitions out from this state here?
so from this state to next one is going to be odd only?
Is going to be what only?
Odd only, if you're looking for odd, say 1, 3 or something.
Okay, but there's no magical odd number input.
Oh, yeah.
That's not a and specifically we said we want some odd number of zeros. So that means 0 or 0, 1, 1, 0, 0, which is 3 zeros in total. but there's a bunch of ones mixed in the middle there. Or some bunch of other characters. In fact, it doesn't even specify the alphabet on here, so it's like some arbitrary number of characters as long as it contains an odd amount of zeros.
So can we say, sorry to disturb you.
No?
Can we say from 1 to, if we pass a 0, the final state would be okay?
Okay, yep. That's a good starting place. So just a 0 by itself, that's not a number of zeros. Bang, we're in an accepting state at this point. Okay, yep. Okay, so if we assume that that's one of our accepting states, what are some other ways that we could potentially get there? Again, it doesn't really tell us what the alphabet is. I'm just going to say for argument's sake, and this would be a reasonable assumption to state, you could say, given an alphabet of 1, 0, because it hasn't told us what our alphabet is, but we know that the alphabet contains at least 1s and 0s, so we could say, all right, for an alphabet of just 1 and 0, or we could say, for an alphabet of all the numbers, and then we would just have to make sure that we figure out what to do with regular numbers as well.
Okay.
Yeah. All right, but yeah, I'm going to add that in. Assume sigma equals 0, 1. Assume my alphabet is 1 and 0. Okay, so a single 0 by itself gets us into the final or accepting state. What are some other pathways that we can get here?
If you're looking for 1, then we can say 2 times 1 will get us to final state. But
Okay, well, let's just focus on the odd number of zeros path before we try to tackle even number of ones. Yeah.
So the question is how can we get to the final state again?
Potentially, yeah. I might just leave this one as a play around with this, and we can revisit it in our review session next week. But we want to think about all of the inputs in the alphabet and think about how each of those inputs impacts the system at the various points in time. Now, we're building an NFA, so we can potentially branch our inputs and say, okay, well, ones can put us here and here, which we might get to. But so, for example, okay, I'm in the initial state and I receive a 1. What should happen? Should that go to an entirely separate state? Should that just remain in the initial state? Does that affect this in some way, shape, or form? I could argue no, so I'm just going to throw this here for the moment. We can come back to it later if need be. So I can get as many 1s as I want, but I haven't received an odd number of 0s yet. I've just received just 1s. And similarly, if I get to here, what happens when I receive a 0? What happens when I receive a 1?
Oh, okay. If you receive 0, you'll go back to initial state.
Yeah, well, we have to go somewhere that's not here because we're no longer an odd number of zeros. So yeah, the initial state seems as good a place as any. Let's just roll with that for the time being. What if we were to get a 1 while we were here?
Okay, that's it. We can go to the next state probably and wait for another 1.
Okay. I'm just going to say for argument's sake that if we get another 1, we can stay here as well. Because okay, so again, we're only focusing on the odd number of zeros. So if you get a question like this, you need to tackle it one part at a time. Don't try to conflate the two parts together. You will get confused. You will just create a system that doesn't work. We have these tools to abstract the system out into separate components and then build the system back up together if we need to. So focus on one part and then handle another part if that's necessary. So here we have a system that accepts an odd number of zeros. End of story. Now let's take a look at a completely separate system that handles an even number of ones. So now, yep.
Oh no, it's working. Yeah, it's working, sorry.
All right, now I think there's some debate as to whether 0 counts as even or not. So but let's say again, assume 0 is even. Assuming 0 is an even number, and then we very much have the same thing here. We have an initial state like so, and then we have another state out here, so a single one takes us there. That puts us as an odd number, this puts us back, and we can have as many zeros as we like at each point. Now technically this does count as an NFA, albeit a disjoint one. So I'm not sure if that's what the marker originally intended, but this collectively is a valid answer, I suppose, for this question. If we wanted to try and merge them together into a single connected system, then how might we do that?
Can't we just pass 1 and 0 by creating another edge state from one side and so other side? Or we can.
Maybe, yeah. I'm sure we can cross these together in some reasonable manner if we wanted to try and combine them, but I would accept this as a perfectly reasonable answer, because even though it is disjoint, there's nothing to say that a NFA can't be disjoint. It's just that we know that it has multiple initial states, it has multiple accepting states, and has multiple transitions. So this would be a perfectly valid NFA. All right. Consider the formal definition of a DFA. Could briefly explain what 5 elements of the 5-tuple definition are. Well, we've already talked about those, but to recap, Q, the set of states, sigma, the set of the alphabet, Q naught, the initial state, F, the set of final or accepting states, and delta, the transition function. All right, using the transition function delta, which of the following helps with defining the string transition function delta hat? So if we'll recall, the string transition function delta is basically, the string transition function is an extension of the transition function, but that takes a string as an argument. You can think of it as like a recursive transition function, where instead of taking a single input character as an argument, you pass it a whole sequence of input characters. The result of the string transition function is the result of the system after it has processed that sequence of characters, as opposed to just one character. So let's see. Which of the following helps defining the string transition function? So string transition function is... okay, so we're looking for the thing that's going to get us all recursive up in here. So and I would say it's this one. Yep, that seems reasonable. Yep, so the string transition function is itself, but instead of S1 through Sn, it's the result of the regular transition function on Q0 and S1, which gives us another state, like Q2 or something, and then S2 through to Sn. So it's like the first transition, but then process that and recursion. So I'm going to roll with that.
Sorry.
Again, I'm not going to be super focused on like the mathematical formulae side of things because it's not something that I focused on throughout the semester, so just bear that in mind, but we are just going through all the questions in this exam, so. All right. I can't remember what this one is. I believe it appears in one sentence at the start of the book, and I think that is the length of a string, or it is the size of the alphabet. And I'm going to bet length of string, and I'm going to say that that is indeed true, because there are 5 characters in that string. But let's find out, because it is literally a single note on a single page right at the front of this book. Bam! Length of a string right there. So yes, that is true. It is 5. All right, with some alphabet sigma, the empty string may not be a string, therefore cannot be in the language of a DFA on sigma. Can never remember this one off the top of my head, people. Again, not going to focus on the maths. I think I'm pretty sure the empty string does not appear in the language of a DFA. So I'm going to say that that is true. Again, things that appear in like one note at the very start of the book. Let's find out. These get me every time, these ones do. All right. Okay, so, yep. Okay, I mean that makes reasonable sense. If you're very confused by what I'm talking about making reasonable sense, okay, so what we're saying here is sigma star is the empty string, and then so it's all strings of all length over a particular alphabet, whereas sigma plus is all strings of at least one character over a particular alphabet, which is true. I don't know if the plus is correct. I feel like you'd want the union symbol, so whether that's true or false depending on the application of the plus symbol there. Not entirely sure. We'll find out. Well, we won't find out because, again...
So you reckon it's also is just a union?
I would say probably, yeah, probably there should be a union rather than a plus, but I could be wrong about that. This is supposed to be set notation. Okay, language of a DFA, blah, 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 is defined as, wow, yeah, no, I don't, guys, oh, nah. Yeah, nah. So again, this stuff appears as like a couple of pages in the very first start of the book, and we haven't really looked at it at all. So I think you're all getting the gist that I'm putting out here. I hope. Draw a DFA that accepts the strings of zeros and ones that contain the sequence 0, 1, 0, not necessarily at the end. That is a question that we have potentially covered throughout this course. Or the one that we've at least striven to answer. So we want 0, 1, 0. Well, that should be fairly straightforward. 0, 1, 0, like so. And we want any string that contains this sequence. So if we make this an accepting state, if we get 0, 1, 0 in that order, in that sequence, that's fantastic. We end up in the accepting state. We want to stay in the accepting state for anything that we get after that. So 0 or 1. But we also want this to potentially appear at the end, so maybe we get like 10 ones or 5 zeros or something, and then this sequence. So we want 0 or 1 at the start. This is the contains pattern for a basic string matching DFA. If we were to, as you just saw, lose that bit at the front, this is anything that starts with 0, 1, 0, because it has to start with the 0, followed by 1, followed by a 0 to reach the accepting state. Other way around works as well. If we have it like this, then it has to end with a 0, 1, 0. It can contain anything we like up until the point that we hit 0, 1, 0, then we reach the accepting state. Now, what is wrong with this picture that I've just drawn?
Initial state, why it needs to be 0 and 1, like self-looping. I just don't understand why we need self-looping 0, 1.
We need self-looping 0, 1 because we need to keep our possibilities open for some sequences of zeros or ones that are not going to immediately be 0, 1, 0. So if I had 0, 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1, 0, I want to be able to accept that same as I would 0, 1, 0, because it contains the sequence. The problem here, of course, is that this is not a DFA, this is an NFA that I've just drawn. So we need a DFA version of this. So let's try this again. Okay. 0, 1, 0, accepting state. Let's try this again. So if we get a 1 at the very start there, we're going to loop back. Okay, and here, if we get a 0 instead of a 1, we are going to loop back on ourselves here because that's the equivalent of restarting with a 0 into this sequence. If we get to here and we get a 1 instead of a 0, then that's given us 0, 1, 1. So we're going to need to reset back to the start here if this is a 1. And wow, this was so much easier with an NFA than it was with a DFA because there's so much room for mistakes here. This is why we did NFAs in the first place, if you remember. Okay, so that's all good. Now, when we get to here, this can actually be the same because there are no outbound arrows from there already. So 0 or 1 both fly there, but we had to fix all of this up to make sure that the system was still deterministic. So that would be our DFA. Maybe like 1 mark for this, but this is an NFA, not a DFA, and you were explicitly asked for a DFA. So just be careful of that. And that was 2019. Questions?
Thank you so much.
All good. Now, in terms of additional revision and practice that you might want to do, and I know everyone's going to be focused on assignment 3, so we'll talk about this again in the revision session next week, which, in case you missed it, we are having a revision session next week on Thursday afternoon during our usual online time for when we would normally have an online workshop, except for the fact that it is SWAT week next week, so there are no classes scheduled. I have not set the location, but we will do a combined in-person online session for that one. So I'll be booking a lecture theatre, maybe this lecture theatre if I can, but I will confirm the location for everyone at the start of next week. But in the meantime, if you want to do some revision, take a look at the past exam papers and also take a look at the questions from workshops, because the questions that you see in there, you may recognize that some of them are from past exam papers, some of them are very similar to questions from past exam papers, and some of them are new questions that you haven't seen for new parts of the course that are completely different than what is covered in the past exam papers. I would make sure that I'm familiar with and can do all of those, because those roughly represent the types of questions that you might see in an exam, within reason. So Obviously, if like a question is asking you to write like several pages of code, it's probably not going to end up in the exam, but you get the idea. So I think that's a good place to start to make sure that you are familiar with all the bits and pieces. And that pretty much brings us around to time for today. So I hope this session has been somewhat useful. Keep asking questions on Piazza, all of the things, and we'll catch some of you next Thursday. Good luck and take care.